Hello everybody, welcome to this course on nuclear and particle physics, coded PhD 7103 in semester 3. We'll see shortly what are the objectives of this course and what are the outcomes. As we know that the course nuclear and particle physics is having 5 modules, so therefore we are supposed to have 5 objectives and is related 5 outcomes. So each one objective and outcome is related to the each module. For example, the first objective, if you consider, it talks about the properties of the nucleus. So that is related to the first module, that is nuclear structure. Likewise, all rest of the objectives are related to the other modules as such. And likewise, we also have slated outcomes which the students are supposed to obtain at the end of the course. So move on. The first module, nuclear structure, is having a syllabus as stated here. So we're going to discuss about some of the important points that I've given here as key topics also visible here. You can see we're going to see about nuclear size estimation, alpha particle scattering experiment, and about magnetic moments of the nucleons in the nuclei, semi-empirical mass formula, mass parabola, and nuclear models. These are some of the topics. Of course, other than these topics also sometimes we may have to see. Well, each class is consisting of in this COVID situation during the online class. Each class consists of 2 periods clubbed together, which means 50 plus 50 minutes is 100 minutes. So given all the 6 topics, we'll be requiring regular 12-hour session, right? Well, once we start, the session would go on for 2 hours, 2 periods together, so therefore one class is of 100 minutes. And this is just for your information. Well, we go straight into the course. So let's discuss some of the basic aspects of nuclei which we already know of. So what is the size of the nuclei? How does a nuclei appear? Right, it appears spherical. And some of the important information we already know about, we studied in the younger classes, but still let's have almost a kind of a recap so that it will facilitate us through the next few topics coming ahead. Well, as the statement reads here, it consists of a nucleus is consisting of positively charged particles mainly, though neutrons are also there. Neutrons are chargeless particles. And we also know that the negatively charged electrons are revolving around the nucleus. So this is also better discussed in the atom model. Well, so what we know of nucleus: a nucleus is the center of the atom, or we can say a small core of volume inside the center of the atom, where there are nucleons, which are the protons and the neutrons. Neutrons are chargeless particles, and the protons are positively charged particles. So therefore nucleus is positively charged. Well, we move on to the next slide. But if you come to know about the magnitude of the charge of electrons, we already know of this, and it is 1.6 10 power minus 19 coulomb. Same way, if you look at the protons, they do have magnitudes of the charge which is almost the same as that of the electronic charge magnitude, which means by magnitude the values are same for protons and the neutrons, right? Except that electrons are negative, protons are positive, and this makes the kind of a balance inside the atom, that if there are 10 protons inside the nucleus, there must be 10 electrons outside the nucleus. This provides the balance. As a result, you have the neutrality of the atom. So atom is electrically neutral, so the charges compensate each other. Well, when it comes to mass charges, we understand protons are having similar charge in magnitude as that of the electrons, but when it comes to mass, the mass of the protons is much greater than that of electrons. So it is said like this: the mass of the electrons is 1 by 1836 times that of proton. Mass of each electron is 1 by 1836 times, which means proton is 1836 times heavier than an electron, which means if electron is 9.1 into 10 power minus 31 kg, proton is not equal to that. It's something else. We'll see what it is in the later slides. Well, so due to this equality of the magnitude of the charges, the atom is considered to be electrically neutral. We already know about this. And electrons revolve around the nucleus and are not randomly distributed, but it was believed that the electrons are arranged in shells. Well, we move on to the next important topic, which is about the nuclear model as suggested by Rutherford, as put forth by Rutherford in the year 1910 or 1910. So he described not only the model, he described the size of the nucleus. He estimated the radius of the nucleus in his experiment of alpha particle striking on a gold tin foil. Well, he did the experiment like this. The apparatus consisted of a vacuum chamber. A beam of alpha particles was made to come from a radium, and it was made to strike on a thin gold foil. And out of this experiment, and the outcomes of the experiments were very interesting, and that even puzzled the many scientists, not only Rutherford, as the outcomes were different. Previously, they thought that the whole of the atom, the protons and neutrons, were distributed everywhere inside the atom. So there was no idea of the nucleus inside the atom. But when this alpha particle experiment was conducted, when they studied about the different scattering that takes place, they were startled. They were puzzled about the outcomes, as there were not uniform distribution of the scattering of alpha particles. So the scattering angles were different. Some were very small angles, some were very small, some were larger. So he could not explain how different scattering angles are possible when alpha particles strike the gold tin foil. Well, so this puzzled, and he went on. And the reason why it was not expected is because of the fact that at the time of Rutherford, the idea of the nuclear structure was different among them. They thought that the whole of the positive charge is uniformly distributed throughout the volume of the atom, not inside the nucleus. There was no concept of nucleus then, so therefore they were kind of puzzled the results of this alpha particle experiment. But they could provide the reasons, and he provided the reasons like this: that when alpha particle approached the nucleus of the gold atom, alpha particle being a positive, they thought that the nucleus of the gold should be of the same charge, only to repel the oncoming alpha particle away. So this could probably be the reason why there were different scattering angles. How this could also be achieved, they explained like this: when alpha particle went very closer to the nucleus of the gold atom, then the Coulomb repulsion is considered to be very large. As a result, the alpha particle could undergo a large level scattering with a greater angle. Whereas when the alpha particle is far away from the nucleus, its proximity, probably the scattering is much lesser. So this is the reason that they could provide. Well, so the whole experiment is detailed in such a way. It has a small derivation here. Let's go ahead with this experiment by Rutherford, the estimation of the nuclear size. In Rutherford scattering experiment, it is really possible to estimate quantitatively the radius of the nucleus. So in which you'll find that we are going to consider the nucleus to have a lot of positive charges. We don't talk about neutrons here because they're not having any charge. So we consider only the distribution of protons inside the nucleus. So the alpha particle is approaching in this direction towards the nucleus, and we have different alpha particles too, right? And let B be the impact parameter, that is the distance of the trajectory of the alpha particle from the center of nucleus is given as B here, which is the impact parameter, right? And R is the radius, it is understood here, though it is not given, radius of the nucleus. Well, what is expected now? When B is very larger than R, when this impact parameter, which means what? The alpha particle is very farther away. When B is greater than R, the deflection of alpha particle is obviously very less. But when B is less than R, when B is less than R, that is within this, this is the radius. So when B is less than R, what happens? The alpha particle goes through the nuclear positive distribution, it penetrates through the nucleus, and as a result, the charges above the trajectory and below the trajectory, they work against each other. And the one that is having a larger charge distribution wins the combination, and therefore it puts the trajectory away from it. And the deflection produced by alpha particle is small, because there is kind of a competition between smaller charges and larger charges. So that is the result to this alpha particle trajectory that penetrates in the upper side of the nucleus. It penetrates, but on the upper side of the nucleus, therefore it faces a small deflection here. Well, let's see the other case. When the alpha particle just grazes the nuclear boundary, where the impact parameter B almost equals to the radius of the nucleus. The impact parameter B almost equals the radius of the nucleus. And then you'll find that the contribution of the Coulomb repulsion from the positive protonic charges is greater level, and therefore the alpha particle is also getting deflected to maximum level. So that is what is actually seen. And let us consider a particular trajectory of the alpha particle in order to be able to derive for the radius of the nucleus. So what we consider here is a trajectory almost straighter here, and then it gets deflected by a small level. And as the particle approaches the nucleus of the gold, you find that it is getting slowed down. Why it gets slowed down? As it tries to penetrate through the nucleus, alpha particle being a positive, they are repelled by the present positive charges inside the nucleus. But then the alpha particle wins, and it passes through, penetrates through the nucleus, and when it comes out, they are being pushed away with a greater force by the same positive charges of the protons inside the nucleus. They push the alpha particle out. So what you can see here is in the experiment, when alpha particle is entering to the nucleus, it is being slowed down. As it crosses the midway region and comes to the other side, they have been speeding up on its way out of the nucleus. So this is how we can explain the Coulombic repulsion. And if you try to evaluate the Coulombic repulsion between these two charges of the protons of the approaching alpha particle, we could do so by considering the Coulombic force F, which we normally know is the product of the magnitude of two charges. One charge is ZE is because we do not know how many number of charges inside the nucleus. For iron it could be 56, for different elements it is different. So therefore we keep Z into E is the charge of the proton. And what is the other particle? The other particle is approaching alpha particle, whose charge is 2E, because an alpha particle is nothing but the nucleus of the helium atom. So there are the two protons in it. So therefore 2E. So 2E into ZE, or the magnitude of the charges undergoing the impact. So 4 divided by 4 pi epsilon naught. The distance is, you can find this is the distance. So B square, the impact parameter square. Well, so here it is described. 2E is the charge of the alpha particle, ZE charge of the nucleus. Well, gold is atomic number is 79. So this repulsive force is acting in a direction perpendicular to the incident direction over a distance B. So how would it act? The repulsive force would act in this direction, try to push the trajectory out of its way. So therefore it acts along this direction. So that's what is stated here. So let us now consider, if this alpha particle has a velocity v, the time during which the Coulomb force acts can be evaluated. So let's call that time a very short period of time. So delta t, which is equal to b by b. What is that? If you put the velocity on this side, put the delta t underneath, you will find velocity is equal to distance by time. By what distance the trajectory of the alpha particle is pushed out of the nucleus, the distance is b under the time period of delta t, and already the alpha particle is traveling with velocity v. So therefore we can easily say time period is equal to distance by velocity. Well, during this there is a change in the momentum of the alpha particle. If the alpha particle has a velocity v, it should also naturally have a momentum, and as a result what happens is that there is a change in the momentum, right? And this can be seen over here. It has been deflected. Change in the momentum is delta p if p is the momentum. Well, so by Newton's law, by F is equal to ma, we can write this as we know that a and m can be altered such that it looks takes the shape of a momentum. So therefore F is equal to dp by dt, we know this. F is equal to ma can be rewritten as F is equal to dp by dt. Here we have delta p by delta t. Keeping delta p over here on to the left and taking force on the right side, we have evaluated what is force, the Coulomb force acting between the alpha particle and the nucleus with a positive charge. Well, besides that, we also have found out delta t. So if you substitute these values over here, if you see here, delta t is v by v, and the force we have already defined it as the product of the magnitude of the two charges over the 4 pi epsilon naught distance square. So we substitute everything in place here. Therefore we define delta p, and then from which we can easily get to know what the deflection is, because the deflection here, if you note down from this diagram, theta is equal to opposite by adjacent. If we put tan theta, if we can use, and for small values of the angles we can consider tan theta equal to theta. So theta shall be equal to delta p by p. So that's what is written here. So having said that, delta p is value is written here divided by p, and there is a b square over here and b here. Parameters, impact parameters will cancel, so one square is cancelled off, and therefore we'll have only b here, and there is a v here, and then there is a p down, so that p is multiplied. As a result, this p is written in terms of mass into velocity, which means it gives you mv square. So p is coming over here. So theta becomes this value from which you can take the impact parameter out. So the impact parameter b is written like this. Theta goes down, this theta goes down, and b comes over here as a result. So b is written like this: 2z square z square by 4 pi epsilon mv square into 1 by theta. If theta is supposed to be 1 radian, and if you consider even impact parameter is exactly equal to the nucleus of the radius, then p shall become equal to r, because if you just go back to this, if b is exactly equal to this radius, which means when the alpha particle almost grazes the boundary of the nucleus, touches the boundary of the nucleus, and then it will experience a maximum Coulombic deflection. Scattering angle will be greater. So let's consider that kind of a case here, where b is equal to r, theta is taken as 1 radian, then you'll find r is equal to 1 by epsilon naught 2z square by mv square. So we know the substitution of these constants value, z equal to 79 mass, alpha particles mass is substituted here, and you get to know, you finally reduce down to r value approximately equal to 10 power minus 14 meter. So this is extremely very small when compared to the radius of the atom. Radius of the atom is around 10 power minus 10 meters, you can find here. So therefore we can make a comparison here that the radius of the nucleus is smaller than the radius of the atom by a factor of 10,000, so 10 power 4, right? More accurately, even the radius in most of the nuclear problems, you'll find that they are given as Fermi, where 1 Fermi is equal to 10 power minus 15 meters. That is the most precise.